Hello dear student, welcome to the E-Pathshala in the Department of Physics, Shri RLT College of Science, Akola. This is our lecture number 6 in which we will study about the simple pendulum. Myself Shailesh Jaiswal, Assistant Professor, Department of Physics, Shri RLT College of Science, Akola. So in this lecture, we will discuss about the simple pendulum. So first we see the definition of the simple pendulum. Simple pendulum is defined as a heavy point mass suspended by a weightless, inextensible string from a rigid support. Now I will show you the practical demonstration of the simple pendulum. Let us suppose this is a heavy metal bob. Okay, this is a heavy point mass. Here we consider this is a bob having mass m. Okay, it's a heavy point mass suspended by a weightless, inextensible string. This is a suspended by the weightless or inextensible. Here weightless, it means that the weight of this string is very small as compared to the bob, so that it says a weightless. So the weightless, inextensible. Inextensible, it means that it is not an extensible string. Okay, the length of the string is fixed during this experiment. Okay, so weightless, inextensible string from a rigid support. So one end of the string is attached to the rigid support and another end of the string is attached to the heavy point mass. Okay, and this type of system is called as simple pendulum. Okay, we say as a simple pendulum. So once again we repeat this definition. Simple pendulum is defined as a heavy point mass suspended by a weightless, inextensible string from a rigid support. It's called as, the system is called as simple pendulum. Okay, now let's draw the diagram of this simple pendulum. Okay, this is a rigid support. One end of the string is connected to the rigid support and another end of the string is connected to the point mass. Having mass is m and the length of this string is considered as a L. Okay. Now we displace this point mass with a small angle. Let us suppose we displace this point mass, okay, and creating a small angle theta here. Okay, we displace this small heavy point mass and then release. Then what happened? It performed, once again, it performed a simple harmonic motion. Okay, it performed an oscillation along its mean position. This is a mean position. Okay, this is a, your mean position is considered as a O. This is a here the point which is suspended. Okay, it performed the oscillation along its mean position. So we can draw this displacement position here. Okay, displace with a small angle theta, and it start to oscillate along its mean position. Okay, now here m is the mass of the bob and L is the length of the simple pendulum, and it displays with a small angle theta. Okay, so now at the displacement position, so here in the displacement position of the bob, the force acting on a pendulum R. See here what happened. We we want to find out the time period and frequency of this simple pendulum. So we know this is a heavy point mass, and we studied its motion. The motion is oscillation. Okay, so if we study its motion, we need to find out its time period. Okay, so we know the formula for the time period. Time period T is equals to twice pi by omega. Okay, omega is the angular frequency. If you know the angular frequency, then we have to find out angular velocity or angular frequency, if it says, if we know the omega, then we have to find out its time period. So in this experiment, our aim is to find out the time period of this simple pendulum. This is the definition, this concept. Now we'll find out its time period. Okay, for finding the time period, we study this simple pendulum. Okay, so in the displacement position of the bob, so this is the displacement position here. This is the displacement position. Okay, so at the displacement position of the bob, the force acting on a pendulum. So at that displacement position, two forces acted on this pendulum. One force is acted downward, called as weight, the gravitational force Fmg, acting downward. And second force is tension T in the string. Tension T in the string. Okay, so this is the displacement position. At the displacement position, two forces acting on this pendulum is, one force is gravitation force, which is pulled downward to this bob. It means that the force is nothing but its gravitational force, or here we say as a weight of this bob. So the gravitational force mg, or we say as a w weight, acting downward, and another force tension T in the string. Okay, now the situation is that these two forces, tension T on the string and weight mg, is not, they are equal but not in opposite direction. In generally, what happened, this is a, suppose this is a point of mass which is placed somewhere. Okay, the gravitation force acts on this bob to the downward direction, mg, called as its weight, and this object is balanced due to this surface on which it is placed. So the two forces act on this object. One force is gravitation force, which is acting vertically downward, and another force is called as normal reaction, which is acting vertically upward. So these two forces are equal and opposite, so that we compare this force N equals to mg. But in this situation, these two forces, tension T and tension T on the string and the gravitational force mg, but they are equal but not in opposite direction. So in that situation, we can resolve this component into the two components according to the or using the law of parallelogram of vector addition. You know, this is a parallelogram. Okay, this is a one vector we say as a p, and another, this is another vector we say as a q. The resultant of this two vector is nothing but is diagonal. This is a resultant. Okay, p vector, q vector. Resultant of this p and q vector is r. So according to this law of parallelogram vector addition, here we use, and we can resolve this one resultant into the two this component. So let us consider this mg is a resultant, and we can resolve this resultant into this two component. Okay, so here one component and this is another component. We written as weight mg can be resolved into the two components. First, a mg cos theta. Here we written as a mg cos theta, the radial component along the string. This is a radial component along the string. Okay, and mg, this component mg sin theta. So mg sin theta is a tangential component perpendicular to the string. Okay, this is a perpendicular to the string. So mg sin theta is a tangential component which is perpendicular to the string, and the mg cos theta is a radial component which is say along the string. Okay, but now here the tension T on the string and this component mg cos theta both are equal and opposite direction. So in that case, the component mg cos theta balanced by the tension T, and this component tangential component mg sin theta, this component this component, it's try to return the bob on its original position, mean position. Okay, so mg sin theta is nothing but we can compare this mg sin theta is equals to the restoring force when we displace this bob with some angle. Okay, so the restoring force try to return this heavy point in its original position. So the direction of restoring force toward the mean position. Okay, so the direction of restoring force is balanced with this component mg sin theta. So therefore here we can written as once again we written the tension T is balanced with this mg cos theta component, and the restoring force F is equals to, we can written minus mg sin theta. Okay, here negative sign indicate that this theta, angular displacement and force are in opposite direction. So here we can also written as a theta. Why we written as a theta here? Because this and this angle are both are same, because these two are parallel line. Okay, and now here dot is diagonal, this angle and this angle alternate angle, so this angle and this angle are same. So F equals to minus mg sin theta, negative sign indicate that the restoring force F and the angular displacement are in opposite direction. Okay, so now if theta is very small, it means that is approximately or less than equals to 6 degree. If the angular displacement is very small, near about 6 degree or less than 6 degree, so in that situation or in that case we can written as sin theta is equals to theta only. So therefore this force can be written as F equals to minus mg into theta. Okay, now so now this equation can also be written as here, therefore F by m is equals to minus g into theta, and we know that according to Newton's second law, force equals to mass into acceleration. Okay, or acceleration A is equals to force by m. So we can written as here F by m nothing but the acceleration is equals to minus g theta. Okay, so this consider as now this theta is an angular displacement. We can convert this angular displacement into linear displacement. So see here, we know that the theta is equals to arc upon radius. We know that theta is nothing but the arc upon radius. So here this is angle theta. So theta is nothing but is arc. This is our arc upon radius. Radius is L. Okay, so this is a displacement from this mean position. Here we turn it as x. Okay, this is our x is nothing but our arc, and L is the radius. Okay, this is circular arc and this L is a radius. So that here we can write it as angular displacement theta is equals to arc upon radius. Arc is nothing but x, radius is nothing but L. So theta equals to x by L. So this acceleration once again can be written as acceleration is equals to minus g into x by L. Okay, or acceleration can be written as minus g by L into x. This considered as equation number 1. Okay, so now this is a pendulum. When we displace it, then it perform a oscillation. It nothing but, so that it means that it perform a to and fro motion along its mean position. So it is nothing but a simple harmonic motion. So see here in this diagram, if we displace this bob, this is original mean position O, we can displace this bob at position B and then release. Then it perform oscillation from B to O, then O to A, once again A to O and then O to V. Okay, so it starting from B and return to the B, so that it performs one oscillation, and the time required to complete a one oscillation is nothing but its time period. We will find out it. Okay, so we will find out the formula of this time period. So this is nothing but the oscillation. So the pendulum perform the simple harmonic motion. So we already know in the previous lecture we see for the simple harmonic motion the formula for the acceleration. Therefore, for SHM acceleration we know that it's a minus omega square x. This is considered as equation number 2. Now compare these two equations. General acceleration formula of the simple harmonic motion, and this is the acceleration of this simple pendulum. If we compare the equation number 2 and equation number 1 and 2, so therefore it can be written as from equation 1 and 2, we can written as minus g by L into x is equals to minus omega square into x. So here minus minus sign get cancel, x and get cancel. Therefore omega square is equals to g by L, or omega is equals to under root of g by L. This is the angular velocity is equals to g by L, and g is the acceleration due to gravity and L is the length of the pendulum. So therefore periodic time t is the equals to twice pi by omega. Therefore t can be written as twice pi upon under root of omega is omega is nothing but under root of g by L. So therefore t is equals to twice pi under root of L by g. This is the time period of simple pendulum. T equals to twice pi under root L by g. Okay, twice pi is constant, L is the length of the pendulum, and g is the acceleration due to gravity at that position where we perform the experiment. Okay, so by using this formula we have to find out the time period of the simple pendulum. This is a theoretical formula, and the frequency of the simple pendulum F equals to the reciprocal of time period. This is the frequency and time period of the simple pendulum which performing the simple harmonic motion. Okay. Now in ideal situation, what happened? If it displays this bob and the release, then it performing the oscillation continuously. But in practice, this oscillation become a damp oscillation because after some time, this amplitude of this motion will gradually decreases. So practically, with respect to time, the amplitude of this simple pendulum is decreases. But in ideally, if we display this once, then release, then it perform the oscillation continuously, not a stop. Okay. Now, once another situation is that if we take one box, okay, and place this system in this box, and remove all the air, or we say as a create a vacuum inside the box, and performing the same experiment. So what happened in the inside this box? The pendulum oscillates. The oscillation of the pendulum continuously. The pendulum is not stopped because no air resistance is there. Because pendulum is stopped due to the air resistance in the environment. But inside the vacuum chamber, there is no air resistance, so that it performs the oscillation continuously. But in practical case, this oscillation or this displacement is amplitude of this displacement is decreases gradually. So this is all about the simple pendulum. Okay. So this is a theoretical formula for finding the time period t equals to twice pi under root L by g. Now in your practical, you have to find out the time period of this simple pendulum. How you have to find out? If we display this bob and the release, and measure the oscillation. Let us suppose it performing the 20 oscillation in 1 minute. We use the stopwatch, and when we displace it, when we release it, then we on the stopwatch and measure the oscillation in 1 minute. So number of oscillation per unit time is nothing but a frequency of this pendulum. So 20 by 1 minute or 60 second is nothing but the frequency of this simple pendulum. So in that way, practical frequency and the theoretical frequency we can match. Okay, so this is all about the simple pendulum. Okay, so thank you very much for watching this video.